All right, guys, we're going to do the work on the night horse problem now so that you can see this kind of online as we continue. The goal of this particular problem will be to find force tension and then force of hinge. We set up the force diagram yesterday, so just a couple quick reminders. Obviously, we have the night horse right there. We have the tension on the cable. We have over here on the hinge, we've split it up into up and left. Of course, that could be combined together later, which I might do off screen to let you work on, because you can see that's just a vector. If I want to find the force hinge along with its angle, I can just take it in two individual components and do Pythagorean theorem and inverse tangent to find those angles. But let's begin with force tension. So up here, you'll notice that two of these things we can find relatively quickly. Also, if you weren't here yesterday, we made up some numbers for us to use on this problem. We have that this angle right here is 30 degrees. We have that the mass of the bridge is 2,500 kilograms, and that the weight of the knight is 1,750 pounds. So, of course, we have to do those numbers differently. Might as well knock those out ahead of time. So let's go ahead and do that now. How do we get force of bridge then, or force of gravity? Well, that will just be mass of the bridge times G, or 2,500 kilograms times G. And I should have had a calculator ready to go. And I don't. So here we go. 2,500 times 9.8. So that is 24,000. Let's write this right. 500 newtons. And then for force, obviously we still need this in pounds, so we are going to have to convert. So 1,750 pounds. Okay. Let's see, it's 1 pound. It's 4.45 newtons. That's 1,750 times 4.45, or 17,000. I'm rounding here. Let's go ahead and round to this right here, so we make it easy. 7,800 newtons for later. So we now know that force and that force right there. Okay. To that end, we also established a couple other things. One, we said that the bridge, let's put this up here, is going to be a total of 5 meters long, and that the knight is currently 1 meter from the end of that bridge. Okay, now, to find this problem, similar to the rabbit problem, you'll notice that we have a bunch of unknowns. In this case, we sort of have 3 unknowns. Okay, we have force tension, we have force hinge in the y, and we have force hinge in the x. So torque is the way to go. Why is torque the way to go? Well, you'll note that there's 2 nice places to put it. We could put it either here. Okay, we could put the fulcrum here, in which case you'll notice both of the 2 of these cause no torque. Well, actually, this one's going to cause no torque anyway, which I'll bring up here in just a second, because the other option is, what am I doing now? The other option is putting the fulcrum here, in which case you might be, well, I have 2 unknowns, except as stated just a second ago, this guy right there is not actually going to cause any torque whatsoever. So let's decide to put the fulcrum here and go straight for tension. So we're going to sum the torques, set it equal to 0. Let's look at all the torques. Again, neither one of those currently cause torque because their lever arm is 0. This guy here is going to cause it to rotate that way. So that would be a negative torque. So we have negative torque of gravity. Night horse is going to do the same thing. So negative torque of night horse. And then you'll see here tension, okay, has a component that way. So it's going to make it spin that way, and therefore is going to be a positive torque of tension. And now, of course, we just go into calculating torque of tension equal to torque of gravity plus torque of night horse, and we use their individual equations. This is going to be lever arm of tension times force of tension times sine theta of tension equals, let's move the screen, lever arm of gravity, force of gravity times sine theta of gravity plus lever arm of night horse times force of night horse times sine theta of night horse. A couple of quick things real quick that I like to do is look for 90 degrees. You will find 2 of them. One is here and one one is here. This one, of course, right there, as we established earlier, is not. So we're going to leave the tension one around, but both of those go to 1. Now we can just solve for this guy right here. So force of tension is going to equal lever arm of gravity times force of gravity plus lever arm of 9 horse times force of 9 horse, all divided by lever arm of tension times sine theta of tension. And let's plug that in. The lever arm of gravity should be 2.5 meters, or half the distance to to that particular gravity. You can actually spot on the left side there our force of gravity that we calculated, 24,500 newtons, plus the lever arm of Night Horse. Well, let's look at the picture real quick. Fulcrum's over here on the left side. The whole distance is 5, and this is 1 from the right side. So the distance from the fulcrum to the force is 4 meters. Times the, what's it, 7,800? Yep. 7,800 newtons. Divided by the lever arm to the tension, well, one side to the other was, as we stated, 5 meters. And the angle should be 30 degrees. So let's go ahead and calculate that. What do we got? 2.5 times 24,500 plus 4 times 7,800 divided by 5 sine of 30. We have 36,980 newtons. Now, to find the other two forces, force in the y and force in the x, again, we could totally move the fulcrum and sum the torques again, except that wouldn't find this guy here at all. So how do we find it? Well, similar to the bunny problem, we are just going to sum the forces. It's just going to do that in both the x and the y. So starting with sum the forces in the x, because it's easier, we have the force hinge is right, so that is going to be positive. Notice these are just standard positive and negatives, right and left. Force hinge in the x. And force tension in the x is going to go negative. And those are the only two. The other ones don't have an x component, so that means they have to be equal to each other. So all I've got to do to calculate force hinge in the x is calculate force tension in the x, which will take a little bit of trig. We're going to take this answer right down here. That's going to be 36,980 newtons times the cosine of 30 degrees. Cosine because, of course, that's adjacent. 30 degrees because that's the angle on tension. And that should be 36,980 times cosine of 30. A weird number. 32,026 or something like that. We'll just round this to 32,000. It's just fine. Newtons x hat. And now, to get the force hinge in the y, we are just going to do the same thing in the y. Now, there are more of those, obviously. We have positive force hinge in the y because it's up. Negative force of gravity. Negative force of Night Horse. Plus force tension in the y equals 0. So now to get force hinge in the y, again, we just do some algebra here. Add that on the other side. Add that on the other side. Subtract that on the other side. And that should give us our answer. In other words, everything up equals everything down. So we add everything down, subtract the one we know, and that, of course, will be what's left. This was 24,500 newtons plus 7,800 newtons minus, we do need to calculate this one. So once again, that is 36,900 newtons times the sine of 30 degrees. That's 24,500 plus 800 minus 36,900 sine of 30. We get 13,850 newtons. Now, this is technically y hat. And once again, I put that to specify that these are components, because as I mentioned at the very beginning, those components, it's been a big problem, my apologies, are here This was the 13,000, I think 13,000 about 900 that we got just a second ago. Y hat, I'm trying to remember what the numbers are over there. And this is the 32,000 newtons X hat. And if we really wanted to know what force of hinge was in total, we would just take that squared plus that squared, square root the whole thing, Pythagorean theorem, and inverse tangent in order to figure out the angle, if that's necessary, but this is where I'm going to leave the problem for right now. So again, we sum the torques, and your two options at the end are to move the fulcrum and sum the torques again, or sum all the forces, this case in both the x and the y.